Hello and welcome back to my Physics Online lecture video supplement series. In today's video, I wanted to go through part of my lecture on 2D kinematics, and specifically I wanted to look at what has happened once you start to break things down into X direction and Y direction, and basically how to actually use these equations to solve some of the 2D kinematics problems. So in class we kind of discussed that position versus time can be split into two parts. One is position in the X direction, one is position in the Y direction, and that this really gives you 6 coupled equations. But basically that's because variables which are the same on one equation are the same in the other equations. So for example, t is the same for all 4 of these. Initial velocity in the x direction has the same meaning whether we're talking about this equation or this equation, and the magnitude of that initial velocity is in fact the initial speed in the x direction, and so on. So what I wanted to do here is look at the geometric approach for solving this position versus time equation. What I have here is the position versus time as a 2D vector. R equals 1/2 vector A t squared plus vector V t plus vector R initial. And what you do is, as with any other vector, you can set it up so that you have a scale. And in this case, you'll notice that R and AT squared and V naught t and R naught all have the same dimension. In other words, if you looked at the units for all of these things, you will get the same units. Specifically, you will get units of meters. So you'd set up some scale that says something like 3 inches equals 1 meter. Whatever is a convenient scale for you to use. And what you would do is you would draw these vectors out tip to tail. So you'd start off by giving yourself the initial position vector. So here's y, here's x, here's 0, 0. Your initial position is right here at the end of this vector. So to that, you want to add a vector that describes the initial velocity times the time. So we start off at the end of this vector and add another one. If you multiply a speed times a time, you get a distance. If you multiply a velocity times a time, you get a position, or a change in position at least, a displacement. So you can make this second vector on the same plot as the first one. You'd have to be sure to measure the correct angle. So you could almost draw like a little XY axis here and measure the angle from X, as well as getting the length right. In any case, once you've done that, now you take into account the acceleration. For example, if you have an object in free fall, the acceleration will be downwards at 9.8 meters per second squared. So that would look maybe something like this. And what we've done here is that because we've gone tip to tail in each of these cases, we have in fact added these 3 vectors together. And so the vector that starts at the origin and ends at the end of this last vector gives you the position. So now you can measure this angle and you can measure this length, and you actually have the final position at this point in time. This also works when we're dealing with velocity versus time. So all of the vectors in this equation, v equals at plus v naught, are in fact going to have dimension of equivalent to velocity, or equivalent to the magnitude of velocity, which is speed, and so the units will be meters per second. So we choose a scale that says something like 1 meter equals 1 meter per second, or 2 inches equals 1 meter per second, or so on. And again, we'd start off by drawing for ourselves the initial velocity vector. Then we would take into account the acceleration times the time. The acceleration again is going to be straight down, so that next vector should be something that points straight down, and its length is going to be determined by how much time has passed. And if we want to get the final velocity, then we start at the origin and end at the end of this second vector. So this is how you get velocity versus time. Now, both of these diagrams are basically equivalent to having a single snapshot in time. If you wanted to find what the position was and what the velocity was another moment later at a different time, what's going to change? Well, in this first diagram, the initial velocity times the time, if you change how much time elapses, maybe 1 second has passed here, after 2 seconds this thing should be twice as long, so it'll end up over here somewhere. And after that same 2 seconds, this thing will be 2 squared 4 times as long and still downward. So that first one would add to here, and then the second one would end up down here off the screen, and so your final position would connect down here. If you wanted to do for the velocity, this is not changing with time, but this is. So the more time that passes, the longer this pink fuchsia colored arrow is going to get, and therefore this right here, this vector, is going to get pointed more and more downward, and may get longer or shorter as well, depending upon how long this thing is. So for example, after a short time, maybe you end up here, and so your velocity is like this. After a long time, maybe you end up down here, and so your velocity is from here to here. So you'd measure the length of the velocity, and you'd measure the angle around to the velocity, and that gives you the actual velocity thing. So if this is 2 inches equals a meter per second, this right here is maybe 1 meter per second, 2 meters per second, 3.2, something like that. You'll notice that those graphs on the previous slide were not really showing axes that had a position in one axis and a time on the other. Rather, they were showing 2 positions or 2 velocities. So there's actually quite a few types of graphs that you can use to describe the motion of a projectile. So this one assumes that the projectile is moving in 2 dimensions, z and x. So these first 2 are basically showing how is z changing with time and how is x changing with time. These are the most analogous to what you would get if you were looking at this as a one-dimensional motion. For example, our kinematics in 1D with a constant acceleration graph looked like this one. With a constant velocity, it looked like this one. The next thing that you might look at is what's called a space configuration graph. This is basically the kind of graph that would be made, for example, if you were taking a multi-shot photograph of an object as it moves through its trajectory. So you'd get a picture of the object here, then it'd be here, then here, 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 and so on until you've described this parabola. You can also have what's called a hodograph, which is basically showing velocity on each of the 2 axes. That's like the second graph on the previous slide. And then you can also have phase space graphs, which show what's called momentum in one direction and position in the other. The ones that are going to be of most interest to us immediately in this class are maybe these first 4. And in particular, the first 3, although this 4th one is also very useful to us. And these other 2 you will probably encounter in a future class. So I want to work a few short examples just to make sure that everybody's following me so far. I wanted to work a couple of quick or relatively quick examples to make sure everybody's following me so far. In this first example, let's consider you have an object that begins at the origin with a speed of 2 feet per second in the direction of 45 degrees and has no acceleration. And we want to know where will the object be after 3 seconds. This actually is basically a one-dimensional motion despite the existence of that angle and everything. We've been given that v initial is 2.00 feet per second, comma 45 degrees, and we've been given that the initial position is at the origin, so 0 meters, comma, doesn't really matter what we put here, but I'm just going to throw in a 0 degrees. So this is basically the 0 vector, 0, 0. And we're given that the acceleration is also 0. So that's basically 0 meters per second squared, comma, whatever, call it 0 degrees. And at t equals 3 seconds, we want to know what is r. So as a 1D kinematics problem, we might write r is 1/2 a t squared plus v initial t plus r initial, and this is 0, this is 0. So we're left only with this thing right here, and it was 2 feet per second times 3 seconds. So r is going to be 3 times 2.00 feet per second, comma 45 degrees. The only thing that we actually multiply this 3 by is the magnitude part. So we would end up with r equals 6.00 feet per second, comma 45 degrees. Okay, so fairly straightforward there. You could, if you so desired, attempt this in 2D instead of as a 1D thing by doing something like this. This initial, initial velocity is given by 2 feet per second, comma 45 degrees. Can be represented using a diagram that looks something like this. We'll call this the Vy direction. This is the Vx direction. So this thing right here is V. This right here is 45 degrees. This is V equals 2 feet per second. And so this right here is Vy initial, and this right here is Vx initial. So Vx initial is V initial times, since this is adjacent, we'd use cosine of theta. So that's 2 feet per second times cosine of 45 degrees. And so what that's going to give us is 2 times, to do this cosine we do like this, 1.41 feet per second. So V x initial is 1.41 feet per second. Vy initial is going to be v initial sine of theta. So again, 2 feet per second times the sine of 45 degrees. Sine and cosine of 45 degrees are equal, so that means that Vyi is going to be also 1.41 feet per second. So now we would have to do the x position is 1/2 ax t squared plus v initial xt plus x initial, and these two are both 0. So we'd have 1.41 times 3, so 1.41 meters per second times 3 seconds. And so what that's going to give us is 4.24 meters. So x equals 4.24 meters. Y is going to also equal the same thing, plus 4.24 meters, because all the terms are the same in y. So then you'd have to convert back into r comma theta for comparison. Sorry, I've been writing meters. I meant to be writing feet. So these should have been feet per second. So you'd have your y and your x, and then you'd have some vector out like this, and you've been told basically that this is 4.24 feet, and this is also 4.24 feet. So you can do something like, to figure out this length of this one, you might do this guy squared, and there's 2 of it, so you have to add another 18 to that. You get 36, take a square root, and in fact you see you get 6. So that matches with the answer that we got over here at 6 feet per sec. Should have been just 6 feet. It's a position. So 6 feet, and then this angle right here is going to have a tangent that's 4.24 over 4.24. So that means that the tangent of the angle is 1. And as you know, if the angle has a tangent of 1, then the inverse of the angle is 45 degrees. So both methods should get us the same answer, and as you see, both have got us the same answer. Graphically, you can even see that by building the scale and just drawing out the v0 vector. Because r0 is 0, there's nothing to add to this from that, and because a is 0, there's nothing to add to that from that. So this vector is analogous, is equivalent to the vector that you get for the final position. So let's consider another example. Now you have an object which is initially moving with a speed of 10 meters per second in the forward direction and has an acceleration of 9.80 meters per second straight down. So we want to know, what will the new velocity be after 2 seconds? And is it going to be going faster or slower than it was initially? Okay, so let's go ahead and write out that information that was given in the problem. The initial speed, the initial velocity was 10.0 meters per second. Straightforward might be equivalent to 0 degrees. We were also given that the acceleration is 9.80 meters per second squared in the straight down direction. So straight down is usually depicted as 270 degrees. Therefore, we can break both of these into x and y components relatively easily. So the initial velocity is going to be 10.0 meters per second, comma 0 meters per second. This should actually be, if I'm consistent with my notation, a parenthesis. And then the acceleration would be 0 meters per second squared, comma negative 9.80 meters per second squared. Okay, and the question is, what is the new velocity after 2.0 seconds? So v of 2.0 seconds is what? Well, v is always going to be given by v initial plus acceleration times time. So we have basically here two different equations that we can use. One is for the x's, one is for the y's. The vx part is going to look like the initial in x plus the acceleration in x times time. This is 0. So after 3 seconds, it's still moving at 10.0 meters per second in the x direction. For the y part of it, we have basically the y components, which are like so. In this case, this one was given as 0 initially. That's this right here. So what we have is the acceleration, which in this case is minus 9.80 meters per second squared, times the time. The time was 2.00 seconds. So we would need to multiply the acceleration times the time. So 9.8, which was negative, and that needs to be times 2, should be 19.6. So our Vy is minus 19.6 meters per second. So our final velocity so far is written as 10 meters per second, comma, negative 19.6 meters per second. And that technically does answer the first part of the question. That really is a velocity. But the second part was, is it going faster than it was initially or not? So we might as well convert to polar. So I'm going to go ahead and sketch what this thing looks like. So we go 10 this way and minus 19.6 this way. So that vector maybe looks something like this. It's hard to draw straight on this system. So this right here is 19.6 meters per second. This is 10.0 meters per second. We'll call this angle phi. And this right here is v. So v squared is vx squared plus vy squared. So that's 10.0 meters per second squared plus 19.6 meters per second squared. So out comes the calculator. 19.6, even if it's negative, when it's squared, gives us 384. 10 squared, of course, is going to give us 100. And then we're going to need to take a, to get the v squared part, this is fine. So this is 484 0.16 meters squared per second squared. That means that the final speed is actually going to be given by the square root of that number, which is 22.00. And we actually have three significant figures that we'll keep. So 22.0 meters per second is what we can record for our final speed. That is in fact faster than the initial speed of 10. Just for fun, let's figure out what direction this thing's going at. So tangent of phi is going to be Vy over Vx, and we can put absolute values over those if we want. So this is 19.6 meters per second over 10.0 meters per second. So phi is going to be the inverse tangent of that. So 19.6 divided by 10, and then we take inverse tangent and get 62.96 degrees. So let's call this 967. And that is actually this angle here. The actual angle that we want, though, is theta, which is this whole angle around. And so theta is equal to 360 degrees minus phi. So that means that we're going to get a total of 297 degrees, or 297.0 if you want. Okay, so the final velocity done that way is going to be given by 22.0 meters per second, comma 297.0 degrees. And as a double check, this thing should end up in the third quadrant, and of course 270 degrees would be straight down, 360 would be straight along the x, so this thing is between those two. It ends up in this fourth quadrant, which is what we would expect. You can also get to that same result by adding these guys as vectors. So the initial velocity was only in the x direction, was 10.0 meters per second, 0.0 degrees, and that is added to the change in velocity, which is acceleration times time, was 19.6 meters per second straight down. So this vector plus this vector gives us this vector, which is the final velocity. You would then measure what is this angle, or if you'd like, you'd measure what is this angle and subtract from 360, and then you measure the length of this guy to get the magnitude. So let's do what would be a longer example, by which I mean this one was originally written to be solved in a more involved manner. So let us consider something that has it start off at the origin, and the initial velocity is 0 meters per second, comma 1 meter per second. And it has an acceleration of 1 meter per second squared and 0 meters per second squared. What will be the position and velocity of this thing after 5 seconds? Graphically, what that looks like is this. Here is the position versus time vector, in which I've just basically plotted dots for the x, and I've plotted dots for the y. And so after 5 seconds, you would need to basically look at where is the position at 5 for x and where is it for y, and then from there you could get the actual position in polar form by converting from Cartesian to polar. The other way to think of it is, let's combine these data into a XY plot. So the motion looks like this as an XY plot. Basically, this right here is actually a sideways parabola whose peak is around the origin. It won't actually quite be at the origin, but it will be fairly close to it on this scale. In any case, where these dots on this plot came from is that I take the first X and the first Y and I put them together, and that's this first dot, and then the second X and the second Y makes the second dot, the third pair makes the third dot, the fourth pair makes this fourth dot, this fifth pair makes this fifth dot, and so on. So like this pair right here, which is the sixth pair, you can see that X should be at around 12, Y should be at around 5. So we go to the sixth pair, and in fact here's Y at around 5, here's X at around 12, and so on. So that's where this plot has come from. Now, to figure out where the thing is going to be at 5 seconds, we look at which dot does that correspond to. So 1, 2, 3, 4, 5, 6. It's got to be the sixth dot. So that's this one right here. So we would draw a little arrow from here to here. The length of that arrow gives us the magnitude of the displacement. The angle is going to give us the direction. So here's one that actually finds for a little farther out. You'd basically measure this angle and this length. All right, let's go ahead and look at that example though now with solving it using Cartesian, meaning solving it the analytic way, if you will. So the initial velocity was given to us as being 0.0 meters per second, comma 1.0 meters per second. And the initial acceleration, or the acceleration in general because it's not changing, is given to us by 1.0 meters per second squared, comma 0.0 meters per second squared. All right. So, and also the initial position, our initial was given to us as 0, 0, because it's at the origin originally. So we can break this up into the x part, which is like this, and then there will also be a y part, which is like this. So both equations actually look the same initially because we have plugged in no numbers to either one of them. Once we plug in the numbers, that's where the two start to look different. For example, the initial velocity for the x component is 0, so this term goes away. This one is also 0 because we were initially at 0, 0. This is not 0. In the y part, the initial acceleration, or the acceleration I should say, is 0. But the initial velocity in y is not 0. The initial position is 0. So for x, we end up with 1/2 times 1.0 meters per second squared times 5.00 seconds squared. So 5 seconds squared should be 25 seconds. And then we're multiplying that by 1, and then we're dividing that by 2. So you end up with 12.5 meters, which is very much like that roughly 12 that I eyeballed off of the graph. For y, you end up with 1 meter per second times 5 seconds, which of course is 5 meters per second. Again, same as what I pulled off of the graph. So we could write for our final position that it is 12.5 meters, comma 5.00 meters. And I accidentally included some extra units over here. Should be just 5 meters. Now, if we wanted to get the magnitude and direction of that to put in polar, we would need to plot that. So 5 comma 12.5 might be over here somewhere. That's better. So this length is 5.00 meters. This length is 12.5 meters. Alright, so this length we could say is r. This angle right here actually is theta. So r squared is x squared plus y squared. So that's 12.5 meters squared plus 5.00 meters squared. So that 12.5 meters squared is 156.25. Add to that the 5 squared, you get 181.25. So r squared is 181.25 meters squared. Therefore, if I wanted to get the actual value of r, I would need to take a square root. That's 13.46. So we'll call that 13.5 meters. And then the next part is to get the angle. So tangent of theta is opposite over adjacent. So 5.00 meters divided by 12.5 meters. So let's pull that guy. 5 over 12.5 gives us 0.4, and we need to take the inverse tangent of that, gives us 21.8 degrees. So theta is 21.8 degrees. And we'll go ahead and write that up here so that we have our final answer for position in both Cartesian and polar coordinates. Okay, the other part of the question was, what will the velocity be after 5 seconds? So to do that, we will need to recall that velocity is always going to be, so long as you have a constant acceleration, v initial plus acceleration times time. So this thing right here can be split into the x and y's again. So Vx is going to be equal to, we had a 0 for Vx here, so 0 meters per second, plus the acceleration is 1.0 meters per second squared times 5 seconds. So that gives us 5 meters per second. For Vy, we end up with 1.0 meters per second plus 0 meters per second squared, because the y part was 0. So that times 5 seconds is still going to be 0 here, so we end up with 1 meter per second. So the velocity is given by 5 meters per second, comma 1 meter per second. So if we wanted to get that in polar, we would need to make ourselves a nice little diagram like this, and 5 comma 1 probably puts us about here. Got it. So this is 1 meter per second. This is 5 meters per second. So v squared is going to be vx squared plus vy squared. So that's 5.0 meters per second quantity squared plus 1.0 meters per second quantity squared. So the 5 meters per second part should give us 25. Add to it 1 is 26. Take a square root and you get 5.099. So that's going to round off to v is 5.1 meter per second. And then similarly, tangent of phi is going to be vy over vx, where this guy right here is phi. Should actually be just theta v, but in any case, this is going to be 1.0 meter per second divided by 5.0 meters per second, and so phi, or if you want theta v, is going to be equal to the inverse tangent of 0.2, so that's 11.3 degrees. So 11.3 degrees. And if for consistency we wanted to write that over here, that would be 5.1 meters per second, comma 11.3 degrees. And that is our final velocity after 5 seconds. Again, we can try to solve this problem geometrically and or by plotting. So this is showing us both the positions and versus time and the position against position for this example. And again, we came out with an answer that was pretty similar to what we had in the example. All right, let's look at another relatively long example. In this one, we're going to again begin at the origin. This time, our velocity and our acceleration are oblique with respect to our regular xy axis. So now we want to know what is the final position and velocity going to be after 6 seconds. All right, so again, our initial position was given as being at the origin. So it's the 0 vector, 0 meters, comma 0 meters. The initial velocity was given to us as being at 5 meters per second in the 30-degree direction, and the acceleration is given to us as being 2.0 meters per second squared in the 225-degree direction. So, and we're trying to solve for at t equals 6 seconds. So let's convert both of these guys into our polar, from polar into Cartesian. So we have a Vy and a Vx here, and we were given that it is 5 meters, comma 30 degrees, so 5.0 meters per second, and this is 30 degrees. So we want to find Vx and Vy out of that. So Vy goes with this side, Vx goes with this side. Vy is going to be opposite over hypotenuse is sine. So If you want the opposite, take the hypotenuse and multiply by the sine. So that is 5.0 meters per second times the sine of 30 degrees. So let's go ahead and pull that guy up. 5 times sine of 30. Sine of 30 should be a half. So that is 2.5 meters per second. 2.5 meters per second. These, by the way, are the initial. So let's do now for x. Vx initial is v cosine theta because it is the adjacent. So to get adjacent, you take cosine and times hypotenuse. So that's 5.0 meters per second times the cosine of 30 degrees. Cosine of 30 degrees should be about 0.866. So multiply that by 5 to get 4.33 meters per second. So the initial speed in the x direction is 4.33 meters per second approximately. So AX and AY, because really this thing is down here in the third quadrant. So this right here is going to be the AX part of it. This right here is, that's the AY part of it. This right here is the AX part. This is A. These are all initial, of course. And this right here is that initial angle of 225 degrees. This one right here is 2.0 meters per second squared. So the initial for x is going to be the initial times, we might as well just use this interior angle right here, phi. So this whole thing is 225, this part's 180, so phi is going to be 225 minus 180. So phi is 45 degrees. So we use, for x, a initial times cosine of phi. So that is 2.0 meters per second squared times the cosine of 45 degrees. So this initial for x is going to be given by this. I need to get a cosine of 45, so that's 0.707. Got to multiply that by 2, should be 1.41. And it turns out that y is going to be equivalent. Before we put those numbers in, though, notice what quadrant it's in. It's in the negative quadrant, so we might as well put that minus sign in. So it's going to be negative 1.41 meters per second squared. And AY initial is going to follow suit and also be minus 1.41 meters per second squared. Alright, so now we've got all of these conditions, and the acceleration is actually constant, so the initial is equal to the acceleration at all times in this motion. So let's go ahead and figure out what the final position and what the final velocity are going to be. So we'll start with the final velocities first. Let's go ahead first and find the final velocity. So final velocity is whatever is the initial velocity plus the acceleration times time. Okay, so the initial velocity we have, the acceleration we have. This thing basically we might break into x and y. So Vx is going to be V initial x, or Vx initial plus Ax times t. V initial in the x was 4.33 meters per second. To that we're going to add a negative 1.41 meters per second squared multiplied by 6 seconds. So out comes the calculator. This times 6 gives us 8.49. So this whole thing right here is negative 8.49 meters per second. And so the final for x is going to be that plus 4.33 meters per second, so minus 4.16. So negative 4.16 meters per second. To get the y part, we do basically the same thing. V initial y plus ayt, which is going to be 2.5 meters per second, plus this stuff is all the same for y, so minus 1.41 meters per second squared times 6 seconds. So now that means that Vy finally is going to be 8.49 plus 2.5 gives us negative 5.99. So minus 5.99 meters per second. So let's go ahead and put a little space for that here. So the final velocity is 4.16 meters per second, comma, minus 5.99 meters per second. Okay, now what needs to happen is we need to convert this over into the polar. So once again, we need a diagram, something like this. And this one right here is basically down in this quadrant. This is V final. This is Vx. This is Vy. We have Vx and Vy, so V squared is Vx squared plus Vy squared. So that means that the final speed is going to be minus 4.16 meters per second quantity squared plus the 5.99 meters per second guy quantity squared. So V squared is going to be what? We gotta square this guy. To that we're going to add the 4.16 and we're going to square it. We can drop the sign because it goes away with the squaring anyway. It means that the V squared is 53.18. So 53.18 meters per second. And then if you're going to find the actual final speed, you take a square root and it becomes 7.29. So V is approximately 7.29 meters per second. Both of these guys are actually squared. Okay, and then similarly, if you want to find the angle, we'll call this angle phi. And tangent of phi is going to be, in this case, Vy over Vx. Sorry, my labels are a little bit backwards on this diagram once again. Should be Vx and Vy. So this right here is going to be 5.99 meters per second divided by 4.16 meters per second to get the tangent of phi, and so phi is going to be given by the inverse tangent of whatever that is. So let's plug it into the calculator and find out. Okay, so we need the inverse tangent of that. It's 55.2 degrees. So 55.2 degrees. And since phi is this angle right here, and what we need right now is actually all of theta, which is the whole thing, we need to use theta is phi plus 180 degrees. So you take that guy and you add 180 to it to get 235.2 degrees. So 235 degrees. Alright, so now we've solved for what the final velocity is. Now we need to do the same thing but for the final position. Alright, final position is going to be 1/2 times the acceleration times the time squared plus the initial velocity times the time plus the initial position. And the initial position was 0, so we're just going to drop that thing right out. This should be split into x's and y's, so the x part is going to be 1/2 times ax t squared plus v initial x times t. So that is going to be given by 1/2 times the acceleration for x was minus 1.41, so 1.41 meters per second squared times 6.0 seconds squared plus this velocity term, which was 4.33 meters per second. That of course is a positive 4.33. That's times 6.0 seconds. Okay, so the final x position is going to be given by, we've got to plug all these guys into the calculator now. So 1.41, which was negative, divided by 2 times 6 squared. So this first term is a minus 25.38. So let's go ahead and write the minus 25.38 meters in here. And then the other term is going to be 4.33 times 6. So that's 25.98. That's a positive. I'll go ahead and write that here. 25.98 meters. So when you add those two numbers together, you get 0.6. So the final is 0.6 meters of x. Now we have to do the y part. So 1/2 ay t squared plus v initial y times t. So that's going to give us a half times negative 1.41 meters per second squared times 6.0 seconds squared. This thing right here is all the same numbers as in x. I'm just going to stick in that 25.38 meters. And then to that we're going to add in our initial velocity contribution. So the initial velocity was 2.5 meters per second, and that is again multiplied by 6. Okay, so 2.5 times 6 is 15 meters. So let's do it. 25.38 plus 15 should be 10.38, or minus 10.38, I mean. So the final position in y, negative 10.38 meters. Alright, so let's now figure this guy out in polar. So our final, I'll just go ahead and write it up here again, 0.6 meters comma minus 10.4 meters. There's probably some more significant zeros after this. We'll go ahead and do the polar and Cartesian though. So we'll call this y, we'll call this x, and we're basically coming down here somewhere. So long straight line, about as straight as I can actually draw it. And the triangle is going to end up being this thing with a tiny base. So, you know, here's x, here's y, here's r. R squared is x squared plus y squared. This is almost certainly just going to end up being 10.4 again. So square this guy, add to it the x part squared, take a square root, it's still 10.4. So r is about 10.4 meters. And for phi, this interior angle is going to be phi, and this whole thing is theta. So theta is going to be 270 degrees plus phi, whatever phi is, because this is 270 and this right here is to get to phi. So tangent of phi is going to be opposite, which in this case is actually the x, over adjacent, in this case the y. Again, we'll drop the sign conventions. So phi is approximately going to be tiny as hell. Let's plug in these numbers and get the inverse tangent. It's 3.3 degrees. So the final position in polar is going to be 10.4 meters, comma 3.3 degrees. Okay, so at this point we have officially solved the long example. So let's look at what this would look like graphically. You could make plots of position versus time for both x and y. They both have the same acceleration, so both have basically the same shape. The difference is that there is a difference in initial velocity for the x part and for the y part, and so the apex of the x, or the vertex of the x, is shifted with respect to the y. So here's maybe the vertex in y, here's maybe the vertex in x. And other than that, they both describe upside down parabolas with the same acceleration. That's to be expected. Here is basically what the y and x position is going to look like. It actually kind of boomerangs around a little bit because of the direction of both initial velocities and of the acceleration. You could get, for example, the final position by drawing the displacement from 0, 0, which is actually right here, to the final position after 6 seconds. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm doing like maybe 1.5 second increments on these dots, or excuse me, 0.6 second increments on these dots, whatever. You would basically measure an angle and a distance. Probably the actual dot I should have drawn to is the sixth one. 2, 3, 4, 5, 6. So this right here is the actual final position, but to show what's going on, here's a longer arrow. Graphically, what we've got going on here is both positions looking at 1D projections, position versus time for x and for y. The two have the same acceleration. What that basically means is that this one right here and this one right here are going to both be the same upside down parabola. The only difference is that they're going to be shifted a little bit in where the vertex appears. So sort of up and to the right for x with respect to y. This one right here is the xy position plot, and so is basically like taking a snapshot once every second and seeing where the position is. At 6 seconds it is right here, so properly you draw an arrow to here. Again, you saw in the drawing that arrow is going to be a little bit hard to see any real details on. In principle, you could get the position after, say, 9 seconds by drawing from initial to final at 9 seconds, then measuring the angle and measuring the length. You can also do the same thing with velocity. So this is the velocity versus time. This is Vx versus Vy. Basically, because they have the same velocity, the same acceleration in x as in y, you're basically going to get a slope of 1 for this line, with the intercept being determined by this difference in x and y initial velocities. And again, you can draw a arrow from the origin to the position that you might want, or to the velocity that you might want, and get the velocity by using measuring an angle and measuring a length. So to sort of move on a little bit, it's sometimes worth drawing for yourself a projectile diagram which shows both the x and y components of a velocity as this thing is moving. In other words, how are x and y evolving in time? And this is again showing velocities. So initially you have some velocity like this at whatever your initial launch angle is, whatever your initial launch speed is. In this case, we're assuming that the acceleration is entirely in the negative y direction, for example, free fall acceleration. And so you'll notice that the x part of velocity never changes here. And you'll also notice that the total velocity therefore never goes to 0. However, the y component of velocity changes as time passes. And so at the very top of the arc, in other words, at the apex of the thing's motion, the y component of the velocity goes to 0. So that is sort of analogous to what happens in 1D motion. The projectile motion can be described if you have, for example, something that's in free fall after being launched. Then the 2D set of equations for x and for y look something like this. Since g is entirely downwards, that means that the horizontal position is only going to be given by whatever the initial horizontal velocity was times the time plus the initial horizontal position. There's no acceleration in this term. It's entirely linear. The velocity doesn't change, and so this part of the equation becomes kind of uninteresting. You just get 0 equals 0. In the y part of the motion, the position looks like a position versus time with constant acceleration. The velocity looks like velocity versus time with constant acceleration again. And then you get the familiar v final squared minus v initial squared is 2 times acceleration times the distance traversed. Oftentimes the initial velocity is specified in polar, so you may have to convert into Cartesian before you can set up this set of equations. So I want to work one last long example to close out the notes and then give a few questions to ponder before class. So our long example here is that a howitzer fires an artillery shell from ground level at some angle of elevation and given some initial speed, and we want to know what is the maximum height that the shell will attain. In other words, what's the apex of this thing's motion, how long is it going to remain in the air, and how far away is it going to land. In other words, what's the range. And the other part to this question is what happens if the initial angle of elevation is changed from 15 degrees to 75 degrees. So we have to assume no air resistance. In other words, as soon as it leaves the barrel, the shell is in free fall. And this right here is a howitzer. To give a basic outline of what process we're going to use to solve for this problem, we've been asked to determine the maximum height, how long it's going to be in the air, and where it's going to land. So it's useful for us to basically determine stuff in the following order. It doesn't really matter what order we go in for maximum height and time, but you've got to figure out the time that this thing is going to be in the air before figuring out the range. So let's just go in the order that this problem was given. So 1, get the maximum height. 2, we need to get time in air. And 3 is get the range. And in order to solve this problem, it's useful to first of all draw ourselves a diagram of what's going on in this motion. So I'm going to go ahead and do that down here as sort of like a dotted outline. This thing is being fired up into the air. It goes across some distance in space, and it does it over some time, and then it sort of lands somewhere far away. The range that we're looking for is this distance right here. The maximum height would be this distance right here. The time that it's going to spin in the air, well, that actually is something that I can't really label nicely here, but basically, because of how symmetric this problem is, it should take the same amount of time to get up as it should to get back down. So it should be twice as much time as it takes to get to here. There's another way of solving this problem that does not rely on that symmetry, but let's do the symmetry method first. So this diagram, one thing that it lets us do is label immediately what the initial velocity looks like. So I'm just going to draw that as a nice long arrow like this, and it has an x component, it has a y component. So this will be v initial y, this is v initial, this is v initial x, and this angle right here was given as 15 degrees, 15.0. So if you wanted to solve this problem, how would we approach it? Well, to get that maximum height, delta y max or y max, one thing we could do is figure out that we have some equation that says v final y squared minus v initial y squared is equal to 2 times ay times delta y. So we should be asking ourselves, what is the condition for which the maximum height is attained? And that's why I've written this equation here, because the condition is that this term right here, the speed in y, is 0 when you hit the maximum height. So when this is 0, this right here is also going to be equal to the maximum change in height. So delta y max is going to be equal to, we had a negative v I y squared, and we're dividing by 2ay. So VIY squared is something that we need to solve for before we can solve this problem. So when we look back at this diagram, VIY is the opposite of this angle. So that means that we're using VI times sine of the initial angle. So remember that the initial speed was given as 250 meters per second. So this thing is 250 meters per second times the sine of 15 degrees. And so VIY is going to be given by, let's enter that in, so 250 meters per second times 15 degrees sine gives us 64.7 meters per second. So 64.7 meters per second, and that's what's going to go in down here. So we have negative of 64.7 meters per second, whatever this guy is, squared. We're dividing by 2 times 9.80 meters per second squared, and this acceleration is downward, so it's negative. Hence, these two negative signs will cancel. So plug all these things into the calculator. So this right here was our initial speed in y, so we got to square that. We got to divide by 2, and now we got to divide by 9.8 meters per second squared. So it looks like this thing's going to hit a height of 213.6 meters. So the maximum height here is 213.6 meters, and the initial height was 0, so that means that the actual maximum height itself is going to be 213.6 meters. Okay, so we can write that in over here as 214 meters or whatever. So now let's go ahead and solve for how long in the air. So this thing is done. Time in the air. Well, how long does it take to reach this height? There are basically two ways that we can go about solving for this problem. Method 1 is use symmetry. So T air equals 2 times T up, where T up is the amount of time it takes to get to this height. The other option that we could use is use the kinematics equation. Use 1D kinematics. for solving for t, basically we would use y final equals 0, and y final is equal to 1/2 at squared plus v initial yt plus y initial. This is ay. Okay, so either of these two solutions should work to get us the total time up. The total time in the air. This one you just solve for t directly. You're going to be solving a quadratic. Basically, your quadratic equation looks something like this. 0 meters is equal to 1/2 times negative 9.8 meters per second squared times t squared plus 64.7 meters per second times t plus 0 meters is the initial height. So in this case, we actually have a relatively easy equation to solve for because there's zeros here, there's a 0 here. So your possibilities are going to be t equals 0 seconds, which is when it's first launched. So that's not the right solution. And if you do this thing here, you basically can factor out the t. That's where this t equals 0 seconds goes. And what you're left with is minus 4.9 meters per second squared t plus 64.7 meters per second. All right, and that is equal to 0. So basically solve that for t. In this case, once again, this is actually relatively easy to do because you're starting at 0, you're ending at 0. If you wanted to use the symmetry method, by the way, what you'd end up doing is basically you would solve for when is Vy equal to 0. So when does Vy equal 0? And you get that time, and that's time up. You multiply by 2, and you've got the total time. Let's go ahead and finish solving it this way, since I've basically done all the work for it anyway. This right here looks like t equals negative 64.7 meters per second divided by negative 4.9 meters per second squared. So let's whip out the calculator. Since there's negatives in both, I'm just going to drop the negatives because they cancel. And what we end up with is 13.2 seconds. So let's put that in over here. That part's done. By the way, if you wanted to use the symmetry method, you use Vy is V initial y plus AYT. This one right here is 0 when t is equal to t up. That's the amount of time that it spends in the air going upwards. So t up is equal to V initial y over AY, which again is minus 64.7 meters per second over minus 9.8 meters per second squared. So what's that going to get us? 64.7 divided by 9.8 gets us 6.60. So 6.60 seconds, and then t air is equal to 2 t up. So we would take that number and multiply by 2. And sure enough, we get 13.2 seconds. So both ways we get the same final time. Okay. Last part of the question, number 3, was get the range. The range, this right here is really just the range. The range is going to be given by x is equal to the initial speed in x times the time that it spends in the air plus the initial position. This one goes away. So now we need to get v initial in the x direction. So v initial x is going to be v initial times cosine of theta initial. So that was 250 meters per second times the cosine of 15 degrees. So v initial in x is going to be given by 250 times cosine of 15 gives us 241.48. So 241.48 meters per second. So therefore the range x is going to be 241.48 meters per second times the time that we solved for in the previous step, 13.2 seconds. So take this guy and multiply by 13.2 seconds and you get 3,187.5 meters. So x is approximately 3,187.55 meters, or if you want, we can put significant figures in. Based on the numbers given, that's going to be 3,190 meters. Okay, so we just solved this problem for all 3 questions. What's the maximum height, how long is it going to be in the air, and what's the range for a 15-degree angle. The follow-up question was, how do these answers change if the initial angle of elevation is changed to 75 degrees? So in other words, instead of firing like this at a 15-degree angle, we want to fire up like this at a 75-degree angle. And I'm doing kind of a bad job of drawing my dotted line. And so I suppose that we could work back through all of this math again on this video, but I think it's better for you who are watching to kind of work these out on your own at home. The answers, though, are that the maximum height should be quite a bit higher than in the first case because it's being fired almost straight up into the air. The time in the air should therefore be a lot longer than before. And you're going to find out that actually the range in this case is the same as before. So I wanted to leave you with a few questions to ponder. For one thing, if all else was equal, what launch angle do you think is going to result in getting the greatest height attained? And similarly, what launch angle should give us the greatest range? So basically these 2 questions assume no air resistance, the thing is in free fall as soon as it's launched, you're launching across a flat level plane, etc. The third question says, okay, what happens in these first 2 questions if there is actually air resistance? Can we come up with a basic conceptual idea of what changes when the shell is basically being slowed down with an acceleration that directly opposes its velocity? And finally, what happens if the projectile is launched from an asymmetric position, either from the top of the cliff into a valley below, or alternatively from the bottom of a valley up on top of a cliff, etc. So thanks for watching this video. Thanks for watching, and I hope that you find this video helpful.